you, wonderful humans. We're about to start our easiest lecture of the whole year, probably. This is going to be on chapter 3.1 and 3.2. Excuse me. Our topics are matter and physical and chemical changes. So I think we've got this. It's going to be, I don't want to say boring because chemistry is never boring, but it's going to be pretty straightforward. So let's just get started. All right. And like I said, most of this is probably going to be a review from middle school science, and if you took it, ISL. If you didn't take ISL, just make sure you have these vocab terms down. We'll do a little practice with some of it, and we will move on. Okay, so first of all, of course, we need our definition of matter. So that's going to be anything that's occupying space and having mass. Remember that our unit for occupying space is something that has volume, and having mass, of course, is going to be in our mass in grams. Matter is going to exist in 3 states. Yes, that's actually an oversimplification. There are fancy other states of matter, but in everyday life, the only things we really are going to encounter are those solid, liquids, and gases. Plasmas just aren't necessarily as everyday. Okay, that's when our gases, the nuclei of our gases are going to be separated from their electrons, and they basically exist in what's called like a sea of electrons. So don't worry too much about plasma, but I always get questions on it every year. So I thought I would let you know that I'm not crazy. I know it exists. It's just not as relevant to everyday chemistry. All right, things you of course know. Solids, rigid, have a fixed volume and shape. Our ice cubes, our diamonds, our iron bars. I'm not going to spend any more time on that because I have faith that you know what a solid is. Liquids are cool because they're kind of the in-between. They have a definite volume. So like if you put it in a big beaker and then transfer that water into a tiny graduated cylinder, it would be the same volume. It would just look different in the different containers. Like obviously here, the way it fills its container looks different. Our examples. There you go. Gases, no fixed volume or shape. Take the shape of the container and the volume of the container. So this is a little more interesting because you really can't measure a gas just based on volume like you can for water, right? If I have 15 milliliters of water, I can actually convert that into how many water molecules I have, because water at a certain temperature is going to take up a certain amount of space. Whereas that's not true with gases. So I could put the gas from a balloon, and let's say the balloon has a 1 liter volume. I could put that gas into a 100 liter space and it would just fill the container. So you have to measure gas differently. You need to know the pressure and the volume in order to accurately measure how much gas you have. I kept this slide in because we're going to be dealing with what's called particle diagrams, a decent amount in this class. So basically we're going to be depicting what is happening at the molecular level with these little drawings. As you can see in our solid ice, we have, they're close together. They're in a rigid structure. Okay. Whoops. Our liquids are still actually pretty close together. They're relatively dense, but they're able to move past each other. So they're not locked into position like in a solid. And that's why they are going to take the shape of their container. Whereas our gases are going to be further apart. When we draw our particle diagrams, there will be the greatest difference with those gases. So liquids and solids, still pretty close together, just not as organized. Gases are much, much further apart, much less dense. Okay, that was all of section 3.1. So you you successfully finished your first section of chemistry. We're doing another one today because that was too easy. Today we're going to talk about also physical properties. So physical properties are going to be things you can take observations of. Okay, so like usually on the first day of class, we do a lab where I just have you take a bunch of observations and we talk about whether you took enough observations that you could accurately recreate the demonstration and those sorts of things. So for example here, one of our physical properties could be odor, right? Like it smells like roses. That's a physical property. The color, volume, as we said, like your volume of water is going to be a very important physical property of that sample. The state, is it solid, liquid, or gas? The density, that is a very indicative physical property. You can identify a lot of substances based on their density. Melting point and boiling point. So your melting point is going to be when you go from a solid to a liquid. It's also when you go from a liquid to a solid. That is still called the melting point. It's at the same temperature. So like ice melts at 0 degrees Celsius, water freezes at 0 degrees Celsius. So that is at a certain pressure, but that's a physical property of water. So it can help identify the identity of the substance. So for example, in organic chem in college, we used to have to identify unknowns. So we do a lot of tests on them. We could test the density. So we'd weigh a sample and find the volume of a sample. Density is a comparison of the mass and volume. So I could calculate the density. Once I knew the density, that narrowed it down to a smaller group of unknowns. I could put it in our melting point machine and find out what the melting point of my substance was. That would further narrow down my unknowns. These are things that we can use to identify substances. Chemical properties. These aren't really as things that you would think of as much when you look at something. Most of the things that when you look at a substance, you think of physical properties. Chemical properties are going to be how they are able to change into new substances. So I'm assuming most of you have seen like those YouTube videos where someone throws a piece of metal into a lake and it explodes, right? Those are going to be our alkali metals. They have a chemical property of being extremely reactive in water. So that's going to be how it reacts with other materials. Characteristics describe the behavior. So flammability, that's going to be how it changes chemically. The rusting, is it rust proof? That's a chemical property that people care a lot about for material goods. They want things that aren't going to rust. How easy something is to digest is going to be a chemical property. Maybe you want to have a food that doesn't digest well because then your body doesn't get as many calories out of it. And then it could be like a diet food. All right, concept check. Your turn. So we are going to have you try to classify each of the following as a physical or chemical property. So ethyl alcohol boiling at 78 degrees Celsius. Is the boiling point of ethyl alcohol a physical or chemical property? The hardness of a diamond, and sugar fermenting to form ethyl alcohol. So the ability of sugar to ferment, is that a physical or chemical property? Okay. Hopefully you answered that 1 was a physical property, so was 2, and that 3 was a chemical property. 1 and 2 both just talked about observations you could make. 3 talked about how sugar is able to change, so that's going to be a chemical property. All right, very closely related. We're going to be talking about physical changes versus chemical changes. So physical changes are easiest to identify because it's relatively easy to undo the change is one way to think of it, or that your substance is not chemically different at the end. So the most common physical change we'll talk about are phase changes. Okay, so boiling, evaporation, deposition, which is the opposite of sublimation. All of these phase changes, so changing from one phase of matter to another, are going to be physical changes. Chemical changes means your substance becomes a new substance. So when iron rusts, it becomes iron oxide. It is no longer just iron atoms. So that's a chemical change because it doesn't have the same identity anymore. When I add baking soda to vinegar, it changes identities. Okay, you see the bubbling, you see a chemical reaction. There's usually signs of a chemical reaction there. Whereas if I put sugar in water, that is a physical change. All that happened is that the sugar dissolved. If I boiled away the water, the sugar would remain. So those two things have not combined chemically. Hopefully that makes sense. An example. So electrolysis, so boiling water, if I just put a pot of water on the stove, I make steam. Steam is still water. It's just gaseous water. So that's a physical change. If I run an electric current through water, which is called electrolysis, I actually split. So there's water up here, and we run electricity through it, and oxygen gas forms here, hydrogen gas forms here. We have split the molecule into its component elements. So look here, our waters became gases. They're component elements. So this is a chemical change because we don't have any water at the end. At the end, we have hydrogen gas and oxygen gas. So chemical change. Here is a practice. Which of the following are examples of chemical change? And you can put as many or as few as you would like. All right. So B is the answer here because when you burn wood, you actually do a chemical reaction. It's called a combustion reaction. Your hydrocarbon turns into a lot of carbon dioxide and water, believe it or not. I'll prove it one day to you guys. The other three are physical changes. Pulverizing or crushing rock salt just makes it smaller pieces. It is still rock salt. Dissolving sugar and water, we still have sugar and water. They're just combined. They're not chemically combined. And then melting a popsicle, it's still a popsicle. It's just in liquid form. Classify each of the following as a physical or chemical change. Do that. All right. So you should have for that sugar fermenting to form ethyl alcohol is going to be our chemical change. Sugar is becoming something else. Okay. Iron metal melting. Now you'd have to have a lot of heat for this to happen, but it is just making liquid iron. So that's a physical change. And then iron combining with oxygen to form rust. We're forming rust, which is a new compound. So that would be a chemical change. And that is all I have for you today. I know that was not a ton of information. Hopefully that you understood that. Please, please, please email me any questions you have over that material, and we can talk about it in class on Thursday.